And what we're looking at now is what we call the amount of substance. All right, so the first heading we're going to look at is molar volumes of gases. Okay, now when we say a molar volume of gases, we say that 1 mole of gas occupies 22.4 cubic decimeters of space, right? At standard temperature and pressure. Okay. Now this standard temperature and pressure we're talking about here is a condition. And this 22.4 is what we call a volume constant. Okay, this you're going to find on your formula sheet. Okay, now when we talk about standard temperature and pressure, it's a condition of a reaction. We're saying that if a reaction has a standard temperature and a standard pressure, then 1 mole of that gas will occupy 22.4 cubic decimeters. If it is not at standard temperature and pressure, then this is not possible. So this whole situation here is not possible. Right? It is not possible for gases not at standard temperature and pressure. Okay, and how we're going to use an acronym is we're going to say STP. So if you see standard temperature and pressure or STP, then you're allowed to use 22.4 cubic decimeters. All right, so let's just have a look here. What do we actually mean by standard temperature and pressure is we say that standard temperature, just write it out. Please make sure you highlight this. So when we say something is at a standard temperature and pressure, the temperature has to be 0 degrees Celsius, or we say 273.15 Kelvin. That's a capital letter K, and that stands for Kelvin. This over here is degrees Celsius. Okay, so that in order for something to be at standard temperature, it must be either 0 degrees or 273.15 Kelvin. Now pressure must be at 1 atmosphere. And how we write that out is 1 atm. Now 1 atm is equal to 101.325 kilopascals. So don't forget the K needs to be a small k, capital PA. So that is the measurement. It's called kilopascals. Right? So when something is at standard temperature and standard pressure, then these are the values that correspond to, and we're going to need those values because we're going to substitute them into formulas, but they're constants. So it's not something that I would say don't not know it. You must know them so that you can substitute it. So let's say if I looked at a fully gaseous reaction. Let's say I looked at H2, which is a gas, plus N2, and we've seen this one before, which is a gas, gives me NH3, which is also a gas. And I say that this is at STP. Okay, I mustn't forget to balance this equation. That's going to be 2, and that's going to be 3, right? So now how this reads is, right, it will be, so how this works is that over here, I've got 3 moles of H2. And if I have 3 moles of H2, it will occupy a volume, because it's at STP, a volume of 67.20 cubic decimeters. That's a point. Okay, I've got 1 mole of N2, which will occupy a volume of 22.4 cubic decimeters. And I've got 2 moles of NH3, and that will occupy a volume of 44.8 cubic decimeters. So here you can see the rule. The rule says 1 mole of gas occupies 22.4 cubic decimeters at standard temperature and pressure. So if this reaction to make ammonia was at STP, then I could say that 3 moles occupies 3 parts of the volume. 1 mole occupies 1 part of the volume, and 2 moles occupies 2 parts of the volume. That is what we mean by standard temperature and pressure for molar volumes of gases. And the next topic we're looking at is molar concentration of liquids. A typical solution is made by dissolving some solid substance into a liquid. So in order to get a solution, I need a solute, which is a solid, plus a solvent, which is a liquid, and I'm going to get a solution, right, which is a mixture that's in the phase is aqueous, which we did last year. Right, so the amount of substance, which is the solute, right, so if I say the amount of substance dissolved in a given volume of liquid is the concentration. Okay, so we say that concentration is defined as moles of solute per unit volume, which is a capital letter V, of solution. Please highlight this definition. So that gives us rise to our formula, which is C is equal to N over V. Right? So in this formula here, C is the concentration, is equal to the number of moles into a given volume. Our moles, we know the SI unit is mole. Volume, we're always going to use cubic decimeters. I'm going to show you the conversion now. And concentration is measured in moles per cubic decimeter, like that. Right? When it comes to conversions for volume, you have cubic centimeters and you have cubic decimeters. Cubic centimeters is the same as saying milliliters, which means cubic decimeters is the same as saying liters. So milliliters and liters. So if I want to go from cubic centimeters, just do the, change colors. If I want to go from here to here, cubic centimeters to cubic decimeters, then I need to divide by 1,000. And if I go from cubic decimeters into centimeters, I need to times by 1,000. Now our standard unit for this section for volume is cubic decimeters. So you cannot substitute into this formula cubic centimeters. Your calculation will be incorrect. So all we're saying is concentration is the measure of the amount of solute that is dissolved in a given volume of liquid. And it gives rise to this formula, C is equal to N over V, which you need to make sure that you recognize and are able to work with it. I'm going to do a few examples with you. Let's start with example number 1. Okay, before we go into the examples, another word you're going to come across is molarity. It is this amount of substance in a certain volume of solution. So when I'm looking at molarity, it has the exact same definition as concentration. So if they ask you for the molarity of something, they're asking you for this concentration. It's just a different word that you might see in different textbooks or in an exam or a test. So please make sure you write it down, and you write down that molarity is just another word for concentration because it has the exact same definition. Let's have a look at that example. Okay, it says here, if 3.5 grams of sodium hydroxide, NaOH, is dissolved in 2.5 cubic decimeters of water, what is the concentration of the solution in moles per cubic decimeter? Right, so the first thing I want to do here is I want to write down my information. Right, I know mass, which is 3.5 grams, and I know the volume, which is 2.5 cubic decimeters, and what they want is they want the concentration. Okay. Alright, so if I look at my formula, C is equal to N over V. Now remember I said you can only have one unknown. Do I have the concentration? No, I don't. Do I have the number of moles? No, I don't. Do I have the volume? Yes. So that's all I have. So what I've got to go do now is I've got to find some other information. So the information that I have is I've got sodium hydroxide. Now the minute they give me the formula for something, I can automatically find its molar mass. And I have other formulas. Don't forget I have N is equal to little m over big M, which is same, it's looking for moles. And I've got N is equal to NP over NA. I've already got two formulas that I can recognize. So now I've got molar mass. So all I have to say is 23 plus 16 plus 1. And my molar mass of NaOH is equal to 40 grams per mole. Okay. Now I've got mass and molar mass, which can allow me to find number of moles, which I can then use in this formula. So all I'm going to do is say N is equal to little m over big M. The little m is 3.5 grams over the molar mass, which is 40. And you just have to pop that into your calculator, and you should get 0.0875 moles. Now you keep all the decimals because that's not your final answer. We're going to take this and substitute it into that formula. So now I've got C is equal to, I know the moles is 0.0875 divided by 2.5, and the concentration is equal to 0.035 moles. Now I want to make that rounded off to 2 decimal places. I want you to just make a note here. If there are many decimals, like 0.00341, something like that, I want you to try and put this into scientific notation. Because if I had to round off this, I'm going to get 0.00. And that makes no sense as an answer. Also, I have to keep 2 decimal places, so I'm in a pickle. So what I want you to do is when you see too many zeros, put it into scientific notation, you will get a better answer. You cannot have an answer of 0.00. That just doesn't make sense. And you can't hold more than 2 decimals. So put it into scientific notation. So C here will be 0 is equal to 0.04 moles. That's acceptable. That would be the final answer. So just make sure here, if there's too many zeros, you scientific notation it so that you're in a better position. All right, let's have a look at the second example. You have a 1 cubic decimeter container in which to prepare a solution of potassium permanganate. I've given you the formula. Please remember, in exams and tests, we may not give you the formula, so please make sure you know how to name. Right? What mass of potassium permanganate is needed to make a solution with a concentration of 0.2 moles per cubic decimeter? Right. So the first thing I want to do here is I want to write down all my information because there's a lot going on, right? I have a volume of 1 cubic decimeter. I have potassium permanganate, KMnO4, which means I can work out the molar mass. Okay. They're giving us the concentration, which is 0.2 moles per cubic decimeter. And they want the mass. Okay. So if I look at my formulas, I've got C is equal to N over V. Okay. I've also got N is equal to M over M. Because I'm looking for the mass. That's what I want ultimately. Now, in order to get that, I've got the molar mass, which I'm going to calculate now, but I don't have number of moles. Okay. But I do have a formula that has concentration, which I've been given, and volume, which I've been given. So I can use this formula now to get that value over there. So that's the first thing I want to do. I'm going to say C is equal to N over V. So C is equal to N over V. And my concentration is 0.2. I don't know the moles, and the volume they're giving me is 1. So my number of moles is equal to 0.2 moles. Great. Now that gets substituted in to that formula. Now I need to find my molar mass. Please make sure you're taking down the questions so that you have a point of reference. All right, so over here, I want to get my molar mass. Potassium is 39 plus manganese, which is 55, plus 16 times 4. Pop all of that into your calculator and you should get 158 grams per mole. Okay, so that can be also substituted into this formula. All right, so what I want to do is say N is equal to little m over big M. I don't know the mass. I know the moles is 0.2. Mass is what we're looking for, and the molar mass is 158. So the mass here then, just pop it into your calculator. The mass here is 31.60 grams of potassium manganate, KMnO4, is needed. So you can see here I can go from concentration to moles. I can go from moles to mass, mass to moles. It's a conversion system. If the formula has mass and moles, it means I can jump from mass to moles. If it has concentration and moles, I can go from concentration to moles, and so on and so on. I want you to notice here, this question was not at STP, right? It is not at STP. So I am not allowed to use a volume. Here they've given you the volume as 1. I cannot use 22.4. I can only use 22.4 if the situation says it is at STP. That's very, very, very important. And let's have a look at the third example. How much sodium chloride in grams will one need to prepare 500 cubic centimeters of a solution with a concentration of 0.01 moles per cubic decimeter? Alright, so can you see here? This is a typical exam type question. They haven't given you the formula, so you must just know. Alright, so the first thing I want to do is I want to sort out my information. They want mass, right? They want the mass, which I don't have. They've given me a volume here of 500 cubic centimeters. Already I hope you can see that there's a problem there. And they've given you the concentration at 0.01 moles per cubic decimeter. Okay. The only formula I have that relates to mass is N is equal to little m over Bm. Now from there, they gave me sodium chloride, and I know the formula is NaCl. I hope you know that too. So we can just say 23 plus 35.5. You do a little mental math, and you get 58.50 grams per mole. Okay, so I've sorted out molar mass. I don't have moles, but I do have concentration and I have volume. It's a problem with my concentration, so I need to go and sort out my concentration before I do anything else. I mean, there's a problem with my volume. Alright, so I'm just going to convert my volume here. If the volume is 500 cubic centimeters, then I must multiply that. I must divide that by 1000. And when I do that, I'm going to get 0.5 cubic decimeters. Okay, now I can take all of that and put it into my new formula, and I can say C is equal to N over V. We need this N over here. Okay, so the concentration was 0.01 is equal to N over the volume, which is 0.5, and the N is equal to 0.005 moles. Now hold on to those decimals because we're going to substitute it in there. Alright, so what we're looking for is mass. So we're going to say 0.005 is equal to M over big M, which is 58.0.50. And the mass is then equal to 0.29225. Now I don't need to hold on to that. I can round this off because there's enough to 0.29 grams of NaCl is needed. Okay, and that's my final answer. So it's a little bit of a process, or a little bit of steps that you have to take. You can't just do it out of thin air. You have to make sure you do your conversions, you write down your information, do your conversions, sort out which formulas you need to use, what's missing from the formulas, and then you substitute that in. Right, gases and solutions. So wherever we look in real life, we see the importance of mixing things in precise quantities. Cooking and baking, the medicines you take when you're sick, the products you buy, all of these rely on ingredients mixed in a very specific amount. It's not some random thing of just chucking things together. If you want to make something, you've got to be very careful about how you make, what you put into it. Even the amount of product forms relies on how much ingredients you use. For example, if I look at this choc chip recipe over here, it says I need 1 cup of flour, 4 eggs, half a cup of sugar, 1 cup of butter, and half a cup of chocolate chips. And if I do that, I'm only going to make 12 cookies. I'm not going to end up with 13. I'm not going to end up with 15. I'm only going to end up with 12. So if I use this recipe, I can only get 12. But let's say I live alone and I don't want to make 12 chocolate chip cookies for some other odd weird reason. I just want to make 1 chocolate chip. So what I'm going to have to do is, in order to get 1 chocolate chip, I have to adjust my recipe. Now I'll have to have 1/12 of a cup of flour, 1/3 of 1 egg, 1/24 of a cup of sugar, 1/12 of a cup of butter, and 1/24 of a cup of chocolate chips. And that will make 1 cookie. So not only do I have to be concerned with the amount of product, I must also be concerned with the amount of reactants or ingredients I need. So in this chapter, we're going to look at these quantities and how they can be calculated. That's what we call stoichiometry. But first, we're going to look a little bit more in details about gases and solutions. So the work that you've done up to now is quite basic. I know it seems like it's a lot, but it's more basic. What we're going to do now is get a little bit more complex. In grade 10, you learned about writing chemical equations, about information that can be obtained from a balanced chemical equation. And this year, I showed you now that balancing equations, not just random, we need that word moles. In this little chapter or the section we're going to do now, we're going to explore these concepts a little bit further and learn more about gases and solutions and reactions. And we will explore the concept of theoretical yield. In other words, how much can I make if I had everything, all my ingredients? How much am I going to make if I don't have enough ingredients? And how do my ingredients relate to each other in order to form my products? So the first section we're looking at is gases and solutions, right? Now, you know a little bit about gases and solutions. So we're going to just look at something that you've already kind of dealt with, and that's the molar volume of gases. All right, so we know now that 1 mole of any gas at STP will occupy a volume of 22.4 cubic decimeters. All right, this is important. So we're doing more grade 11 work based on this. We know of standard temperature and pressure, that our temperature needs to be at 0 degrees Celsius or 273.15 Kelvin. We know of pressure, that pressure is going to be at a 101.3 kilopascals. Okay. Now, where do we get this from? Now, in an exam or test, they can ask you to derive. So I'm going to teach you how to derive that value. How do we get that? Where does that 22.4 actually come from? So let's say if we had 1 mole of a gas at STP, what volume would it occupy? Now, we know what the answer is going to be. We want to show you how you get the answer. So what we need to do is we need to write down all the values that we know about 1 mole of gas at STP. So I know the pressure is going to be 101.3 kilopascals. I know that the N is going to be 1 mole, and the P for pressure is a small p, right? I know the temperature, capital letter T is the symbol, is 273 Kelvin. Now, it's not like metric with the US and us. Everybody uses Kelvin, so we're just going to use Kelvin. Now, the formula that we get from this, right, is the ideal gas equation. Okay, so the ideal gas equation is PV is equal to nRT. Okay, so I'm just going to break it down for you, where P is the pressure, and we're going to put in pascals. Okay, so that you can already see we have a little bit of a problem. The V over here is the volume, and that's always in cubic decimeters. The N over here is the moles. T over here is temperature, and temperature we're working in Kelvin, right? And R over here is called the gas constant, and you'll find it on your formula sheet, and that value is at 8.31, right, joules kilograms per kilogram per mole. You don't need to know the SI unit. You need to know what this value is. And the value is for R. Okay, so that's what we have here. Okay, now what I want to do is, I want to find the volume. I'm looking for this volume, so I need to substitute in. Now, if I'm looking at my values, right, my pressure is in Pascal, so I've got to convert that value. So this value here for pressure, I'm just going to convert it. Kilopascals times it by 1,000 is 101,300 pascals. That's the value we substitute into this formula. So what we're going to do is, everything that we know, we're going to put it into this formula. So I'm just going to start here, so it's fresh. PV is equal to nRT. And you can see very clearly which is my small letters, which are my bigger letters. Now my pressure is 101,300 times my volume, which I don't know. My moles is 1 mole of gas. My R is 8.31. And my temperature is 273 Kelvin. All right, I want you to pause the video, put this into your calculator, and find me the volume. All right, if you pause the video, you would have noticed that you get 22.4. Right? So all we have to say is that this is where we get the 22.40. If I have 1 mole of gas at STP will occupy 22.4 cubic decimeters of space or volume. That is how we get that. So please make sure you understand here when we're talking about whatever the case is, just remember that this is how we get the 22.4. They're going to ask you this in an exam or test. It is a 4 or 5 mark question because you are in grade 11 now. They're asking you to derive that value, to derive the constant. This is how you're going to do it. You're going to write down your formula. You're going to substitute your standard pressure, your standard temperature, your 1 mole of your gas, your constant, and then you're going to solve for volume and get your final answer. So please make sure it is standardized. You don't have to learn it from scratch. I'm showing it to you. You're going to use it just like that. Right. Now, another thing is, if we had any number of moles of gas at STP, any number, which means I can have 7 moles, I can have 2.3 moles, I can have 37 moles. Then all we do there is we say the volume of any gas is equal to 22.4 multiplied by the number of moles of that gas. That's how we do the conversion. So for example, if they said, what is the volume of, let's say, 2.3 moles of hydrogen gas at STP, then all you would do is you would say Vg is equal to 22.4 times Ng. Okay, I'll put it a bit better for you. Times Ng. And then you would say 22.4 times 2.3. And the volume of that gas would be 51.52 cubic decimeters. That's all you're doing. All right. So we know that 1 mole occupies 22.4, but if I had 7 moles or 10 moles or 37 moles or 500 moles, then I could easily work out what volume those moles would occupy by using this formula. And some of these formulas are not on your formula sheet. You've got to memorize them. You've got to know them. So please make sure you write it down and you memorize it. Okay, the next thing is reactions and gases. Some reactions take place between gases. For these reactions, we can work out volumes of the gases using the fact that volume is proportional to the number of moles. We use the following formula, right? New formula, please highlight it. And it's VA is equal to A over B times VB. VA is the volume of substance A, and VB is the volume of substance B. In other words, I can take two substances that are in a question and compare them to each other because volume is in proportion to the number of moles. So that's something maybe you should just highlight, that volume is proportional to the number of moles. So if I know the number of moles, I know the number of volume, the amount of volume. All right, so VA is the volume of A. All right, VB is the volume of substance B, whatever substance B is, you're going to compare to, right? A, little a, is the stoichiometric coefficient of A, and B is the stoichiometric coefficient of B. Now, this little tip at the bottom, important, please make sure you write it down. It says here, the number in front of a reactant or product in a balanced chemical equation is called the stoichiometric coefficient or the stoichiometric ratio. We also know it as the number of moles. So please make sure you get this down, and I'm going to do an example with you. Alright, so the first example looks like this. It says hydrogen and oxygen combine to form water. If 3 cubic decimeters of oxygen is used, what volume of water is produced? Alright, so the first thing you need to do is you need a balanced equation, which means you need to know the formula. Hydrogen and oxygen, they're not telling you it's diatomic, but we know better. We know it is diatomic. So H2, which is a gas, plus O2, which is also a gas, is going to give me H2O. And it's a gas. It comes produced as steam. Right. Once that's done, you need to balance this equation. So when I'm balancing, the oxygens don't balance. So I mean the hydrogens balance, the oxygens don't balance. So what I need to do is sort that out, and it changes my hydrogens, and that's my balanced equation. So the first thing you need to do is write an equation, or let's say write a balanced equation. Now here's the problem. If you don't know how to write formula and you don't know how to balance equations, you can't do this whole section. It's just plain and simple, just like that. Because you need to use the coefficients. You balance incorrectly, you use the wrong coefficients, you get the wrong calculation. So this is very, very important. So now in this question, we have to identify the two things they want us to compare. They're saying that if 3 cubic decimeters of oxygen is used, what volume of water is produced? So what we're looking at is your relationship between O2 and H2O. Those are the two things we're comparing. So what we want to do is we want to identify what's what. So if I'm looking at my formula, if I'm looking at my formula is VA is equal to A over B, VB. Okay. What I'm looking for is VA. So I'm going to make H2OA, and I'm going to make O2B. All right, so let's see what we have. We have VA, VB, A, and B. Those are our variables that are in our formula. So we just need to see what we have. All right, so for VA is H2O. We don't have its volume of A. We do have the volume of B at 3 cubic decimeters. We know A's value is 2, and we know B's value is 1. Alright, so all we want to do is substitute that into the formula. So VA we don't know, A is 2, B is 1, and VB is 3. Alright, so 2 over 1 times 3, and VA is equal to 6 cubic decimeters. Nice and basic. Right, so when I'm looking at this equation, it's not just basic. You've got to do a little bit of work. Now, how do we interpret this? Okay, so there are two ways in which we can interpret, because we're saying that volume is proportional to the number of moles. We can write this or interpret this equation in two ways. The first thing I can say is that 2 moles of hydrogen. This is important. Please make sure you're getting all of these notes down. reacts with 1 mole, oops, 1 mole of oxygen to produce 2 moles of water. That's one interpretation of it, right? A second interpretation, I can say that 2 volumes of hydrogen reacts with 1 volume of oxygen to produce 2 volumes of water. That is how I can interpret that kind of setup. Because whatever moles I have the same volumes. Moles and volumes are proportional to each other. All right, let's have a look at another example. Okay, let's look at this example. It says, what volume of oxygen at STP is needed for the complete combustion of 3.3 cubic decimeters of propane? And they've given you the formula. Now, sometimes we're going to give you the formula because you don't know organic chemistry yet. You get to grade 12, we don't. Right? Hint, CO2 and H2O are the products of combustion reactions. All right, so the first thing we need to do is we need to write a balanced equation. All right, so I know for combustion, I'm just going to give you, it's a fuel plus O2 is always going to give you H2O plus CO2. Okay, that is for all combustion reactions. You know this from last year because you learned this last year. So you need to go back to chemical change so you can sort this out. So you can have C3H8, which is a gas, plus O2, which is a gas, gives you CO2, which is a gas, plus, just make that a bit smaller, H2O, which is also a gas. And you can see all the constituents here are gases. And what I want you to do is pause the video and balance by yourself. Try and balance it by yourself. Double check your balancing. And then we'll move on from there. This is important. It's something you haven't seen since last year. It's good practice. Sit and balance it first before you press play again, for your own good. Okay, so if you've balanced, this is what you should have. Okay, so what they want you to do is they want to know what volume of oxygen at STP is needed for the complete combustion of 3.3 moles of propane. Okay, so now you have to write down your formula, right? So VA is equal to A over B, VB. Okay, so that's your formula. So now you have to decide on your information. They've given you, they want the volume VA of oxygen if they're giving you the VB of propane. So now you need to substitute that into your formula. So your V of O2 is equal to A over B, V of propane, which is C3H8. So V of O2 is equal to the coefficient of A, which is 5, over the coefficient of B, which is your propane, which is 1, times the volume of propane, which is 3.3. So you pop that into your calculator, and the volume of oxygen that you need is 16.50 cubic decimeters. Okay, so in the previous videos you learned about solutions, and I gave you the first formula. And the first formula is C is equal to N over V, where C is the concentration. And that is in moles per cubic decimeter. N over here was the number of moles. And that was in mole. And V over here was volume. And that was in cubic decimeters. Right, then we have a new formula, which is C is equal to M over mv, which is also a relevant formula, where C is still the concentration in moles per cubic decimeter. M over here is the mass, which is in grams, big M over here is molar mass, which is in grams per mole. And then V over here is volume, which is still in cubic decimeters. Okay, so this is what we're looking at here is we're looking at the molar concentration of solutions. Okay, now when you have a solution, what you're looking at is a substance that's been dissolved into another substance. So when I'm looking at solutions, I can say that the molar concentration of a solution is the number of moles of solute per liter of solvent. Okay, so in essence, what we're looking at, or what we understand by when we're using solute, this is the solid and your solvent is the liquid. So your solid are usually salts or fats, and your solvent is usually water or alcohol. Okay, so this is important per liter. So that gives us our SI units. So I can understand it like this. 1 cubic decimeter is equal to 1 liter. 1 liter is equal to 1000 milliliters, and 1000 milliliters is equal to 1000 cubic centimeters. So therefore, if I want to go from cubic centimeters, which is what they usually give you the information in, into cubic decimeters, then I must divide by, so to do that, I must divide that by 1000. And that will give me my conversion. Okay. Now, when we're looking at calculating the molar concentration, so this molar concentration that we look at here, calculating the molar concentration is useful to determine how much solute we need to add to a given volume of solvent in order to make a standard solution. Okay, now that standard solution, so your definition of a standard solution is a solution in which the concentration is known. So just say it like this. The concentration is known to a high degree of precision. When we work with the standard solutions, we can take the concentration to be constant. That is an important definition. Please make sure that everything that's on these slides or in this video is inside of your book. So we're going to look at an example on how we use a standard solution, or how we do calculations using these formulas and so on. Okay, so if I look at this example, it says how much of sodium chloride in grams will I need to prepare 500 cubic centimeters of a standard solution with a concentration of 0.01 moles per cubic decimeter. So the first thing I want to do is write down all of my information. The first thing I know is I have NaCl, and they want the answer in grams, which means I need to find the mass. They've given you a volume here of 500 cubic centimeters. They're telling you it's a standard solution. And they're telling you the concentration is 0.01 moles per cubic decimeter. Okay, now you have two formulas that you can work with. You can either work with C is equal to N over V, or you can work with C is equal to M over MV. Okay, now when I look at these bits of information, I need to see which formula is relevant for me. So if I look at C is equal to N over V, I have the concentration. I don't have number of moles. I do have the volume. But they want the answer to be in grams. If I go to my second formula over here, I've got concentration. I need the mass. Technically, I've got molar mass because I know I have NaCl and I've got the volume. Okay, so in these two formulas, I can use either method. I'm going to show you how to do both, and then we go from there. Right, the first thing that needs to be sorted out is this volume. Right, the volume is not appropriate because it's in cubic centimeters, so I'm going to go 500 divided by 1,000, and that's going to give me 0.5 cubic decimeters. Okay, so I'm going to go into my formula and have a look at how I'm going to sort this out. So, if I use method 1, I've got C is equal to little m over big M times V. My concentration is 0.01, which is equal to the mass, which I'm looking for, over the molar mass of NaCl. So all I've got to go there and do is 23 plus 35.5 times 0.5. Okay, and now I have to just solve for M. And over here, if I solve, if I just pop that into my, put it straight into your calculator, and you're going to have M is equal to 0.29, 29 grams of NaCl is needed. Alright, now if you didn't use this formula, you could do method 2. Please get down both methods so that you're well versed. You've got C is equal to N over V. Now I know that if I have the number of moles, I can use N is equal to M over M to find the mass. So I'm going to do two calculations. So I've got 0.01 is equal to N over 0.5. So the N over here that I have is 0.005 moles. I then need to take that information and I need to go N is equal to little m over big M. I've got 0.005 is equal to little m over my molar mass of NaCl, which is going to be 23 plus 35.5. Put that into your calculator, and mass is equal to 0.29 grams of NaCl needed. So I could use either formula and still get the same answer out of it. Right, titrations is something you're going to come up with now while you're in grade 11. A titration is a technique for determining the concentration of an unknown solution. Titrations can be done using many different types of reactions, like acid-base reactions, which are called neutralization reactions, and redox reactions, which are called oxidation, reduction reactions. Right, so in a titration, I'm going to show you the experiment. Alright, this experiment here is a titration experiment. What we do is we take an acid solution and we drop it into a solution which we don't know the concentration of. We put an indicator inside of it. We have a burette, and that burette releases our base into it, and what happens is the acid and the base mix together and we get a neutralization reaction. So when performing a titration, we say that the substance of unknown concentration is titrated with the standard solution. So the solution that is inside the conical flask, the blue one, that is the standard solution. A pipette measuring device is used to measure the exact amount of liquid. If you use a pipette to add liquid to a flask, when you say that the liquid is pipetted into the flask. So this is what a titration experiment looks like. I expect this experiment to be drawn into your books. When we do acids and bases later, it will be easier for us to understand how the acid-base reaction takes place. Now, we can reduce the number of calculations we have in a titration by using the following equation. So the equation we're going to use is CaVa all over A, which is equal to CB VB all over B. Alright, so in this situation, C of A or CB is your concentration in moles per cubic decimeter. VA or VB is your volume in cubic decimeters, and A and B are what we call the stoichiometric coefficients. Now the stoichiometric coefficients come from the balanced equation. Right? It's the coefficients that we have in a balanced equation. So let's have a look at an example on how to use this formula. Alright, given the equation NaOH in aqueous, HCl in aqueous, NaCl in aqueous, and H2O, which is a liquid. 25 cubic centimeters of a 0.2 moles per cubic decimeter hydrochloric acid solution was pipetted into a conical flask and titrated with sodium hydroxide. It was found that 15 cubic centimeters of the sodium hydroxide was needed to neutralize the acid. Calculate the concentration of the sodium hydroxide. Right, so first thing you need to check is the equation balanced? So if I check the NAs, there's one of each Na, that's fine. OH, there's two hydrogens on the left-hand side, two hydrogens on the right-hand side, one oxygen on both sides, and one chlorine on both sides. So the first thing is the equation is already balanced. So technically, the coefficients that are in front here is just a 1, an imaginary 1. We'll need it for our formula, but you don't need to put the 1, it's just there. The next thing we need to do is we need to check our information. So we've got HCl, which we've been given information about, and we've got NaOH. Right, for the HCl we were given 25 cubic centimeters. So we were given a volume of 25 cubic centimeters, and we were given a concentration of 0.2 moles per cubic decimeter. And for the NaOH, we were given a volume of 15 cubic centimeters. Okay, so the first thing you need to do is you need to make sure you do all your conversions. Okay, so our volumes are not correct, so we need to make sure that the volumes are sorted out. So the volume of NaOH, volume of NaOH, we're going to say 15 divided by 1,000, and that's going to give us 0.015 cubic decimeters. The volume of hydrochloric acid, that we're going to go 25 divided by 1,000, and that's going to give us, please make sure you take down the question, otherwise there's no point, right? 0.025 cubic decimeters. Okay, the next thing you need to do is they want you to calculate the concentration of the sodium hydroxide. So what we're looking for is the concentration of NaOH. So the next thing you need to do is you need to write down your formula. So you've got CaVa over A is equal to CB VB all over B. So what you want to do is you want to put in what you actually working with. So you have your concentration of HCl multiplied by your volume of HCl all over the coefficient of HCl is equal to the concentration of NaOH multiplied by the volume of HCl of NaOH all over B. Okay, so now you know what your C values are. Your B values all relate to NaOH, and your A values relate all to hydrochloric acid. So now all you've got to do is put that into your formula. Your concentration of the HCl was 0.2. Your volume was 0.025. All over 1 is equal to your concentration of NaOH, which we're looking for, multiplied by 0.015 all over 1, because that was your coefficients. So all you're looking for now is the concentration of NaOH. So what you're going to be left with is 0.005 is equal to 0.015 multiplied by the concentration of NaOH. And you're solving for the concentration of NaOH, and that's going to give you 0.33 moles per cubic decimeter of NaOH. Please check my subscripts. So that's how you work out a titration calculation. So please make sure that you take down the question over here, you do your conversions, then you enter it into the formula and you solve. And that's the last video, which needs to be completed by Thursday.